Hello students, today we will read about the electric fields. So, we are having a charge Q in our vicinity, right? This is our charge Q and we want to deal with this charge, and this is placed at origin. This is placed at origin. Now, this is our another charge Q, small q, which is brought near to this capital Q charge. Now they are at a distance of r, centimeter or meter, whatever we want to take as the unit. So they are away with a unit distance of r. Now this small q will feel a force from capital Q. There will be a force on charge small q due to capital Q, on force small charge due to capital Q. Okay. Now what we did, we removed this charge. We removed our small q charge. Removed. Now what is left here in this vicinity? In this area, what is left? Is it a free space? Isn't it like there isn't anything available here in this area? Just think, is there something here? So this is not free space. This is not a free space. Not a free space. This charge capital Q have its influence around itself. So when we bring this small q charge near the capital Q charge, what happens? The small q charge feels a force which is happening due to the capital Q, and similarly our capital Q also feels a charge, like a force due to the small q charge. So the early scientist, the early physicist gave us the concept of electric field. The concept of electric field to define what is exactly happening and why is it happening. Like when our scientist, our physicist gave us the concept of field, they told around the capital Q charge there are line of forces. Line of forces. I will write it. Line of forces. So when we bring any charge from distance near the capital Q charge, these charges feel some kind of force due to the presence of these lines of forces. Similarly, the small q is also a charge. It also have its own line of forces. Okay. When this small charge again brought near the capital Q charge, it will also exert some force on capital Q. So both the charges will have a mutual force fields. Okay, and it is defined on the basis of line of forces. The surrounding of any charge isn't free, like it is not a blank thing. They have line of forces in it. Now coming to the point number 1 here. Let us consider a point charge capital Q placed in vacuum at origin O. If we place another charge small q at the point P, where OP equals to R, This is the distance between origin and point P. Distance between origin and point P. Then the charge capital Q will exert a force on small q as per the Coulomb's law. So as per the Coulomb's law, what is the force that will be experienced by the small q due to the capital Q? It is given as K small q into capital Q upon r square, the distance between the point O and the point P. The charge Q produces an electric field everywhere in the surrounding. So we understood from this, like, it is not a blank thing, it has something which makes the small q to feel some force, and that are electric field lines which are present everywhere. All around the charge electric fields are present. So when another charge small q is brought at some point P, the field there acts on it and produces a force. Electric field produced by the charge Q, charge capital Q at a point R, is given as, like, at a distance of R at point P, okay, is given as E at R equals to 1 by 4 pi epsilon naught R square into capital Q into R cube. This is an extra R square, delete it. Like, it should be E equals to K Q by R square. This is our source charge, where R cap is given as R bar divided by R. What is R cap? Unit vector. Unit vector are given as vector divided by its magnitude, vector upon magnitude of the vector, magnitude, okay, a unit vector from the origin to point R. Now before we move ahead, let's see the diagram, figure 1 and figure 2. See, in figure 1, these rays, these lines are going outward, away from the origin, away from the origin, away from origin, okay. So what which kind of charge we have placed at the origin? Can you see that? It is a positive Q charge. Our charge have positive polarity. So away from O, in the case when charge placed at origin have positive polarity. Now come to the figure number 2. See what polarity charge is there. The polarity of the charge is negative. Negative polarity. So what is happening with the field lines? They are moving near the origin, moving nearer to origin, that is inward motion, inward motion. Here what is the motion? It is outward, it is outward. Here we have inward motion. So these field lines are coming inside the charge. So when we have a positive charge and a negative charge, from positive charge these electric field lines will go outwards, whereas at the negative charge, these field lines will come inside. These field lines will come inside. Here also in similar way, coming out, and for negative going inside. The word field signifies how some distributed quantity, which could be a scalar or a vector, varies with position. Field doesn't vary around, like, it varies according to the magnitude of charge, but it also varies according to the distance from the charge. Okay. What exactly happens is, like, we are having a charge here Q, and we have placed our test charge over here Q, then test charge over here Q. This distance is from the origin, it is R1, and this distance is R2. If R1 is greater than R2, then according to the field equation, E will be smaller, E1 will be lesser than E2. Electric field lines are more powerful near the charges and are less powerful away from the charges. Their magnitude decreases as it goes away. It varies according to which law? According to inverse square law. Inverse square law. Effect of charge has been incorporated in the existence of electric field. We obtain the force F exerted by a charge Q on the charge small q as F equals to 1 by 4 pi epsilon naught into Q into small q divided by R square into R cap. This is again Coulomb's law. Coulomb's law defined for charge capital Q and small q. Charge small q also exerts an equal and opposite force on capital Q. As we have seen in the properties of charges, these charges follow up the Newton's third law. Newton's third law. So this small q is not simply sitting in the electric field of capital Q, but it also exerts equal and opposite force on the capital Q. If the position of charge Q is denoted by vector R, then it experiences a force of F bar equal to the charge Q multiplied by the electric field E at the location of Q. Okay, so the force at position R on small q is given as Q into electric field at that position. Electric field at that point. Now, understanding it more properly, what we have read for electric field, the formula is given as E equals to capital Q upon R square. What is the formula for force? It is K into capital Q into small q into R square. Now, what is the difference between this and this? Only the small q. Okay. So, this is force. This is force. Here, this is force. The value for K Q upon R square will be force upon Q. Force upon Q. So, electric field equals to force upon Q, and then From here the force is given as force equals to charge into electric field. Okay, you may have got it, how the formula is derived. It is derived like this, and from here we get the SI unit of our electric field. What is it? It's Newton per Coulomb. Newton per Coulomb. See, electric field is F by Q. See over the left side, electric field is given by force upon Q. What is the SI unit of force? It is Newton. What is the SI unit of charge? It is Coulomb. So electric field is defined as Newton per Coulomb like this, or Newton C inverse. Okay. Now there are few remarks which we need to understand. From above equation we can infer that if small q is unity, like it is not some x, y or z value, but it is 1. Electric field due to the charge capital Q is numerically equal to the force exerted by it. See, this is our equation. This is our equation. Electric field equals to force divided by Q. When Q equals to 0, when Q equals to 1, what will happen? E equals to force divided by 1, and we will get E equals to force. This is what the statement states. Now, the electric field due to the charge Q, capital Q, at point in space may be defined as the force that is a unit positive charge would experience if placed at that point. So it is defined like electric field, it is defined on Q. Any unit charge which is placed at a distance r, anywhere in the surrounding, like in the sphere of this charge Q, anywhere at the distance of r, if we are keeping a charge here, a test charge here, then the electric field is defined as force that a unit positive charge would experience. Force a unit positive charge would experience, that is the electric field. One important concept which you should know is our capital Q is known as source charge. Source charge, because it is used to produce the electric fields, and small q is known as test charge. Why is it known as test charge? Because we are using this small q to test the electric field in the vicinity of capital Q. Test the electric field in vicinity of capital Q charge. Okay. Now the charge capital Q which is producing the electric field is called source charge, as explained a minute before, and the charge small q which tests the effects of the source charge is called a test charge, where small q is moved near to capital Q, and capital Q tends to move due to repulsion, but capital Q should not move. Hence, to overcome this, let's make Q negligible. So we have few conditions here. Okay, as we say that this small q and capital Q are following Newton's third law. See here on the left corner, we are having our small q, and at a distance of r we are having capital Q, right? Now this exerts some force F, and this exerts some force on small q. So this force due to small q equals to the force due to capital Q. They exert the force which is equal in magnitude, but the direction differs. One comes from right to left, the other comes from left to right. Okay, in this case, when we are bringing this small q very near, like more near more near to capital Q, what happens? They will show some sort of repulsion. And our condition to understand the electric field is that capital Q should not move. Capital Q should not move. It should be stationary. It should be stationary. So, in order to make our capital Q stationary, first step we are taking is that we make our small q negligible. So, the force due to negligible, then the force due to small q will also be negligible, right? Force depends upon the strength of charge also. Force equals to EQ. So, as low as the q is, force is more nearer to capital E. Okay. So, we will make sure our q is negligible to overcome this repulsion. Therefore, capital F force is then negligibly small, but the ratio F by Q, which is equals to E, electric field, is finite, can be defined, and defines the electric field as E electric field, where our small q, our test charge, limits to 0 into force upon q. Second thing, electric field E due to q, though defined operationally in terms of some test charge, is independent of test charge. This E is not like our q is here and these are the electric field lines which are coming from our source charge. I will write as capital Q. We are placing Q1 over here, then Q2 over here and Q3 over here. If the distance of Q1, Q2 and Q3 from the capital Q, Q1, Q2, Q3 from capital Q is same, then all Q1, Q2 and Q3 will feel same magnitude of E. Okay, but if the position is changed, R1, R2 or R3, results won't be same. This all should be equals to R. In this case, we will find that electric field does not vary according to the test charge, but it is purely dependent upon the source charge. What is the source charge? Capital Q. Okay, force on charge Q, see here, due to capital Q depends upon the location of charge small q. Location, that is distance from the capital Q. As you move far away from capital Q, the strength of E will decrease. Thus, capital E due to capital Q is also dependent upon the space coordinates. For different position of small q, for different positions of small q, there exists different value for electric field. If we are 1 meter away from the charge, 1 meter away, it will be something x. If we are 2 meter away, it will be something y. And if we are 3 meter away, it will be something z. Here x will be greater value of electric field, as x will be greater than y and y will be greater than z, because in this case the distance is increasing and electric field have a inverse square relation with distance. The field exists at every point in 3 dimensions. So it gives us what? It gives us spherical. I will write over here. When it is all around in the 3 dimension, it will give us spherical symmetry. Now coming to the point number 3. For positive charge, electric field projects radially outward. Like in the first slide we have seen, the value, like we have our charge over here and we saw like this, the fields are going out. That is for positive charge. This kind of field diagram is for positive Q. Okay. And similarly, see over here, when we are dealing with a negative Q, what is that? We are getting this kind of field lines. The field lines which are getting near to this Q, near to the charge. This is for negative inward, and this is for positive outward. Positive outward, right? Coming to the fourth point, since magnitude of force on charge Q due to the charge capital Q depends upon the distance, of course, as inverse square. Okay, always remember the point, depends as inverse square from small q to capital Q. Thus, electric field E also depends upon R. As I have already mentioned in the previous slide, electric field also depends upon R in the relation of inverse square, Hence, equal distances from the charge will have equal electric field. So, let's see this thing. This is our charge Q and this is equal distance. Okay. I'll make the sphere once again. Just take. So this is sphere. If our charge Q is placed anywhere here, in this it will feel a electric field of E1. But there is another circular thing. In this radius, this is R1. In this radius R2, if our charge is placed somewhere, it will face a electric field of E2. If we go little far from the charge Q, that is charge capital Q, again the distance is extremely away, that is R3. We will denote as R3. If we are giving charge over here, they will have same electric field and it will be denoted as E3. Anywhere on this will have E3, anywhere on this, okay, this line, the line I am trying to cover, this one, okay, anywhere on this line will have electric field E3, anywhere on this line will have electric field E2, anywhere on this line will have electric field E1. So it depends upon the distance. See here, due to the point charge, E is same on the sphere with the point charges at its center. In other words, it have spherical symmetry. So in today's class, we learnt about force and electric field relation, how the electric field behaves when we are introducing a positive charge, when we are introducing a negative charge, how this small q is called test charge and capital Q is called a source charge, and what are the few things which we need to remember when we read about electric fields, like it has spherical symmetry, inward and outward motion in negative or positive polarity of charge respectively, then the force and electric field relation, which states like E equals to force upon Q, or force is given as Q into E, and the SI unit of E is given by Newton per Coulomb. So that's all for today's class. We'll meet in the next class. Bye bye.